the 9t, 0, 1. I mean, that's the general solution in this case. So except in the case that the matrix is very, very silly, in other words, it's the diagonal, if you got a repeated eigenvalue in the 2 by 2 case, more often than not, it's not going to be this. It's going to be the other case that we did, and you're only going to have half the solution, and we'll have to come back to the mystery of how to get the other half later. Again, the other possibility is that you have a 2 by 2 system where you have your eigenvalues are complex, in which case we find a single complex eigenvector, we write down the complex solution, and then we simply pick off the real and the imaginary part. Those are separately fundamental, linearly independent solutions to the problem. All right? But is everything a 2 by 2 system? No. There are also 3 by 3 problems, right? So we should look at those. Let's see here. But I'm lazy, so I'm going to use the projector for those, if that's okay with you guys. Also, because I want to show you the geometry of a particular 2 by 2 system before we're done today. Oh, okay, so you might have been wondering, where's the next homework? I know you guys are like lost without having differential equations homework to do, and I did give practice problems. You could be doing those right from the book, and I'm working on assembling the next practice problems. It's up to about 11 pages at the moment. Oh, I forgot the adapter. So once I sort through that, I should have the next mission up, hopefully tonight, if everything goes well. It will not be due the day after spring break. It's going to be due like Friday of that week, because I want to actually put in not just the eigenvector stuff. I want to also include the what's called generalized eigenvectors on that homework. So the material needs to get a little bit further before I can collect it. And as such, I don't want to make it due the day after spring break. Also, it just seems like a good PR move. I could be wrong, but no, I'm not wrong. Not wrong. See, I could have had that always due the Friday after spring break, right? But by moving the due date from that Monday to that Friday, see how that reflects on me? That's right. See, ever teaching a class, you got to think about these things. You don't tell the goodies at the start. You dole them out bit by bit as the course goes on. This is good pet. I shouldn't really be explaining this to you. This is undoing the goodness of the goodies. Yes. No, I'm saying they were due the Monday after. They were. They were supposed to be. I'm sorry. Yes, good point. They were to be collected. Thank you. The Monday after spring break, but now they're to be collected the Friday after spring break. But which I mean Thursday, because I don't. Yes, I got you. Thursday. I'll eventually remember what day it is. So sorry, guys. Oh man, do I have any laser? I got to find my laser. I got no laser. So I'll have to use a more basic technology. All right, so all right. There are 3 by 3 problems that you guys can solve by hand, and I'm going to give you some in the homework to make sure that you are able to do such. All right. Now, typically with a 3 by 3 problem, the thing that you guys will get hung up on is the characteristic equation calculation. So I'll eventually get to one here. Come on. Where are you going to? Oh, here we go. Here's our first genuine 3 by 3 problem. Here we go. So 3 differential equations and 3 unknowns. Thank you, sir. Let's see how to solve it. So, so it's the same thing we just did, all right? But why is it so much worse? Like I can literally give you any 2 by 2 problem for the test. It's totally fair. There are a subset of 3 by 3 problems that are test fair, and there's another subset of 3 by 3 problems that would just be cruel and unusual punishment to try to get anybody to do on a test, because they're just horrible. And the reason for that is that when you calculate the determinant of a minus lambda I for a 3 by 3, you're up against a cubic equation. All right, so this one, it just so happens that we can factor out a 2 minus lambda, and then this quadratic factors like that. So my eigenvalues are 2, 1, and minus 3. Good news from linear algebra, if you have distinct eigenvalues, here's the thing. You can never find an eigenvalue which doesn't have at least one eigenvector. So if I have 3 distinct eigenvalues, that means I get 3 linearly independent eigenvectors, which means that my general solution is, we're going to find it. The issue is when an eigenvalue is repeated, weird stuff happens. There's a lot of different cases to think about there. But anyway, but the equations are more interesting here, right? So like lambda equals to 1, that gives me this, all right? Which, of course, the top equation is just u equals to 0. That's nice. And then the middle equation, once you know that u is equal to 0, these two equations become the same equation, right? So you can see that the other one is 5 plus w equal to 0, which gives me w is minus 5v, which I can use v as a parameter. We can put v equal to 1, we get 0, 1, minus 5, right? Eigenvalue 2, I do a minus 2i, it gives me this. Now, this time, from this bottom row, I can see 5v equals to 0. And once I know 5v equals to 0, that just means that I've got basically minus u minus w equal to 0 from this other equation. And as such, that gives me this eigenvector. All right? So, point of order here, you never have more eigenvectors than the algebraic multiplicity of your solution. So here the algebraic multiplicity is 1, which means I expect that every eigenvector is a constant multiple of just like the one eigenvector I find here. Of course, the algebra is getting a little bit trickier, isn't it? But not impossible by any means. So here, for eigenvalue minus 3, I'm up against this. This tells me immediately that 5 times u is 0. That's nice. Once I know that 5u is 0, that basically gets rid of this, and I can just focus on these two columns. And at that point, you see that this and that's the same equation. So I'll just keep the 5. Why did I keep the 5 one? Dude, whatever. Anyway, so, okay, fine. So w is minus v, and there you go. So there's my 3 eigenvectors corresponding to my 3 eigenvalues, and the general solution, looky here. Here it is. Same thing we did today, right? But now we've got 3, right? The fundamental solution matrix here would be a 3 by 3. Here it is, all right? And I'm using x sub 1, x sub 2. I've been using r sub 1, r sub 2, r sub 3. This notation is not written in stone. I can't make up my mind from semester to semester. You'll forgive me. I once had very high praise at the end of linear algebra. Some student told me that my notation meant absolutely nothing, and I said, thank you. So, like the highest of praise. Well, anyway. I'm slightly joking. But this one is an upper triangular matrix. Fun fact, if you have an upper triangular matrix, the numbers on the diagonal are the eigenvalues. Because when you calculate the determinant of an upper triangular matrix, you can just multiply the product of the diagonals, like so. And so my eigenvalues are 2, 2, and 3. This one, the eigenvalue 2 has an algebraic multiplicity of 2. So I'll start out, so when we look at a minus 2i, see what happens here? Actually, it zeroes out these 2 rows as it happens, and I'm only left with 1 equation in 3 unknowns. So I have, excuse me, u plus w is 0. Uh-oh. I still got another class to teach. Not good. Maybe we should stop. U plus w is equal to 0, v is free. So u is minus, and so you see this time, unlike previous events, we had 2 parameters in here, which means I can find 2 separate vectors with eigenvalue 2. I can do like 1, 0, minus 1, and I can also do 0, 1, 0 from this one case. The eigenvalue with eigenvector 3, it turns out is just 0, 0, 1. So this problem we can still solve with eigensolutions. We got enough of them, despite the fact. So I want you to notice something here. The eigenvalue 2 was repeated. I have not multiplied the solution by t. You guys get this fuzzy idea in your head that when there's a repeated eigenvalue, you got to multiply by t. That is not the case. We will see how multiplication by t appears in the solutions, but it's much more subtle than that. It's not automatically following just from having a repeated solution. Because, in this case, these two eigenvectors are linearly independent. So these are both from the lambda equals 2 solution, and this is the general solution. That's my fundamental solution matrix. You can check it's invertible. All right? But, come on. Here's another one. This one has eigenvalue 2. Aw, man. So sad. I'm going to get stuck this way if I'm not careful. This one has eigenvalue 2 repeated, just like the last one. So the algebraic multiplicity of 2 is 2. And the algebraic multiplicity of 3 is, whoa. Aw, man, come on. Green cap has let me down. So, but notice that the eigenvalue 2 didn't give me 2 parameters in the solution, right? It turns out I just have 1 parameter, so I only have 1 eigenvector with eigenvalue 2. So what we say the geometric multiplicity of eigenvalue 2 is just 1, right? Geometric multiplicity speaks to how many linearly independent eigenvectors you can find for the eigenvalue. The geometric multiplicity of 3 is also 1 because I just found 1 eigenvector. So in this case, just like my cautionary mystery tale for the 2x2 case, we only get 2 fundamental solutions. Something is missing. Something is missing. And yes, multiplying this by t isn't going to do it. It's not that simple. We'll see what it is after spring break. All right, probably. Actually, who knows? Actually, we're making pretty good progress. We might get to it before spring break. Who knows? Oh, and here's the dumb case. You could have 777 like this. You get eigenvalue 7 threefold repeated. When you look at the a minus 7i equation, it's just 0 equals to a vector. Anything non-zero is an eigenvector. So like in this case, I can write the general solution like this. Basically, e to the 17 times any vector solves this system. Kind of a dumb case. All right, so we'll do more of these next time. What I want to show you before I forget here, while this projector is working, is this example over here. X prime equals to x plus y prime equals to 3x minus y. We might have solved this today already, I think. Maybe that's might have been like my second example, maybe. I forget. But anyway, you have eigenvalues minus 2 and, maybe not, eigenvalues minus 2 and 2. You find the eigenvectors. You get this is your general solution. You write it out. That gives you x equals to this and y equals to that, right? This is the method. What does it mean, though? Like, what's going on geometrically is revealed here. So you can actually introduce eigencoordinates by rotating coordinates using the eigenvectors. And if you rotate coordinates, this system of differential equations simply becomes dx dt equals to minus 2x bar and dy dt equals to 2y bar. In that system of coordinates, it's uncoupled, and it's easy to see how to solve because we can just solve those separately by separation of variables. And if you look at what the solutions look like to this system, you can kind of see what's going on. These are actually the eigenvector directions, like that. And so the solutions either get pulled into the one eigenvector direction or the other, and like, the eigenvectors tell you everything about like the geometry of the solution set and everything. So if you're kind of curious like what's going on geometrically behind this, I've showed you this algebraic method today, right? It leaves you with almost zero geometric understanding of what we're doing. There is a geometric story to tell here about coordinate change and uncoupling. So maybe I should talk more about that some other day. I do have your homework to turn back to you, so let me turn off the camera here and give you your homework. Sorry if you guys were hoping to have the homework due right